Okay, so now what I'm going to do is finish off the start of it. So you'll be able to check your work against this. I'm also going to put in some numbers that you can kind of check. So I think there's somewhere you run your program and you just can check your answer against that rather than have to watch all this video. Anyway, okay. So mechanical testing, blah, blah, blah. So I'm going to go from 0 to 10 in steps of 0.1. So I've started this previously and I'm just finishing it off. Going to 10 seconds. There we go. Label column B, initial velocity, and then put in the code. So the code is the previous plus the step size times the previous slope. Now the lambda over m, so lambda is 1.5 divided by m is 2, that'd be 1.5 divided by 2 is 3/4, that's what's going on there, times v, which is the velocity, it should be the previous velocity, and now if I just double click that, I get what it is. I'm probably going to be asked to graph this. Let's have a look. Now drag the code, produce a plot, and I think with this many points you want to use a smooth plot because it's going to be a reasonable shot. Okay, so here you see that the initial velocity, so this is like a damper, so you think of like a hydraulic thing. So if that's just moving, it's going to stop. And here you see it's got initial velocity and the force opposes the direction of the velocity, causing a negative acceleration and bringing it down to 0. Okay, that's that. And now next one, the design using goal seek. So we've got a similar story. We've got mass 0.1. I think we don't know the damping coefficient. I'm going to change this to 5. Okay, so let's see. In column A, go from 0 to 1 in steps of 0.01. So we need to go down to 1 second here. Okay, and then this is the damping coefficient, and I'd say 10. 10 I think wasn't a good choice, but I will just put in because it should be the same as what you're doing. And it's a guess for the damping coefficient. Now in cell B3, write this code. So this would be the next velocity is the previous velocity B2 plus step size times previous slope. So this is the lambda. D2 with the dollars, which is fixing it, the dollars fix it to this cell. The mass is 0.1 and then its previous slope, so it's proportional to the velocity, so I need to go to the previous slope, which is at B2. And I press enter on that, and then now this is funny because we'll see what happens. It's an unfortunate value of 10 because what it's actually predicting is that it goes to 0 straight away, which is obviously wrong, and that's an error, this kind of thing we talk about in the tutorials. Get rid of that. Interesting. Okay, so anyway, so drag the code down to equal 1, produce a plot. Okay. So we get nonsense really, but that's okay. Now do data. What if analysis, maybe I need to, data, what if analysis, goal seek. So set, now what I want to do is I want to get the final velocity to be very small, 0.01. And what I want to do is I want to change the damping coefficient to achieve that. So if I press OK, it'll go through all the different values. Is it doing well? It looks like it's not doing well. I might have to change it, to be honest, looking at it. Yeah, I seem to be getting issues. Okay, so what's happened here, and fair play, if you get the same error, you'll be like, what's going on? What's going on is that the basically just getting big errors. So what I need to do is change this to something a bit more reasonable. Okay, and then just do the same thing again. So you will learn about this in lectures, that you can have very bad errors here, and it's about when the second derivative is big. And you see, if you look at the lambda, if that's big and you're dividing by 0.1, which is the mass, you're getting, and then you differentiate, you're getting a very big second derivative, which causes problems for Euler's method. If we make the lambda smaller, you're getting a smaller second derivative, it should work better. Well, hopefully anyway. So set cell this thing, I want this to be equal to 0.01, I think I said, by changing D2. Hopefully this will work a bit better. Yeah, that worked better. So like the other one was just a nonsense. There's different ways of getting it, but it was a nonsense. The thing was, our starting approximation was very, very bad. But this is what we wanted. Okay, now we're going into VBA. So I'm going to delete all this stuff because this is not what I need at the moment. And I'm not sure about these command buttons. Well, we'll find out now in a second. Okay. This is what we're doing in VBA. So developer design mode. What does this one do? I think this is what I want. Yeah. Okay. So let's see what we got. So we got double variables t and v. We did that, and a counter. Yeah. We'll start all of them. We did that. Now here we printed the current values. We want to print the current value of v beside it. So cells int row in column 2 to equal to the current value of v. Now what we're going to do is calculate the next v value. So the next v value, dblv, is equal to, this is Euler's method, the previous v value plus the step size, which is 0.1, times minus lambda over m. Now the minus lambda over m we're going to use is the same, minus 3/4, times now dblv. Work fine. And keep going until it's bigger than 10. Now if you're going to run any code, save it before you run it. You can do it line by line, or if you're confident, do an F5. Yeah, looks good. Did we do everything? Okay, now we said about the automatic deletion of data and graphs and highlighting and stuff like this. We'll see that more in the next one. We don't really need it here because we just ran it once. Let's have a look at the graph. I think it'll be the same as the worksheet graph. You might get small, tiny differences in the numbers due to rounding error. Okay, so now in the next one, we're going to change the parameters. So we're going to take our mass and our lambda and our v0 from here. And what I'm going to do here is also, we're going to, we'll see. Okay, so let's see our developer. Let's go into design mode, double click this. So we would have started this. I actually copied the code from the previous sheet straight here. So let's start all these things off. So DBLM, we're going to take from the worksheet. I call this a little dashboard, because what we can do is just change the values of them as we want. 6 DBLM, DBL lambda, which I'm just calling L, cells 2, 7, and then that. Okay, printing the current values. So in row 1, you're going to print the time. That's what's doing that. Also print the velocity, cells int row column 2 equal to dblv. Calculate the next values, that's fine. And now this is the Euler method. The next v is the previous v plus the step size times the previous slope. And again, save it before you run it. And we'll do a little more here in a second. F5, variable not defined. Now that is why you do this option explicit. We actually would have gotten a world of pain here if you didn't have that, because it would have been divided by DLM. And if it's not defined, it's counted as 0. You division by 0, you get errors. So that's why you do option explicit. Stop, save. I have 2 n subs. Third time lucky, F5, here we go. Now, with this one, I think we don't have to do them. So what you can do is you can change the mass. So, or what's the effect if we make it heavier? Do you see what happens there? If it's heavier, it takes more time to slow down. Or if you make the damping not as strong, it'll take longer to slow down. Or if you start it fast, you get a different thing. Say make this very light. Let's see what happens. Now we can get problems. If, for example, if our lambda is too big, so this was like the number we had for the goal seek, this is nonsense. Okay, so what happens here is you'd have to make the step size smaller or use a different method. But that's us done on that. Then the next thing was to, okay, we did the parameters, initial conditions. What about step size also going in the dashboard and the automatic selection as well? Okay, so we're going to do that in, I think, the next one. SSNR, yeah. So we've got our bigger dashboard. Okay, center these. We can take the code from here, to be honest. I mean, these could all be done on the same worksheet. So I'm going to take this, all that code, yeah. I just have to make sure the name of the command button is the same. Yeah, it is. Okay. So here, what's the additional? The additional stuff is the step size and the final time. So we've got two more variables. So dim. Now the step size, let's call it dblh as double, and dim the final time. Now we won't be able to call it dbl big T because little t and dbl big T are going to be the same. Count as the same. So we'll call it dbl final time double. We want to take them from here. So dblh from the dashboard or the console, whatever the hell you want to call it. It's row 2, column 9, and the final time, dbl final time, equals cells to, now here we go. So this now shouldn't be 0.1, but dblh, so we can vary the step size, and then dblh, the rest of this is okay, and we keep on going until the time is bigger than the final time. Okay, I think we have absolutely everything there. And if you can actually get this, you're reasonably good nick for the whole thing. We're just going to be using better methods than Euler's method, at least for a few weeks. But the basic thing, identify your variables, give them initial values, and do a loop where you print the current values and then you calculate the next values. So as usual, save before you run something. Here you go, it looks good. Now what I want to do here is, say if I select this and make a graph. Okay, happy days. What if I want to go for 5 seconds with a different step size and a different starting speed, and say we'll change these as well. And if I try and run it over that, look at this nonsense. So what I want to do is I want to write a macro that will delete the old stuff, because what's going on here is you've got old stuff knocking around. I want to delete the old stuff, put my labels back in, and I don't even think you have to do the automatic selecting because I think the graph is already in tune to that. So we've just seen a bit of this the last day. You go to developer, macros, just record macro. Yeah. So we'll call it delete and graph, delete old or something like that. Yeah. So everything I do now is going to be recorded as a macro in here. So I want to take these, delete what's in there, and I want to put my labels back. I think that's going to be enough. I'm not sure, that we might have to double check. So that module there is called delete old. So we'll put that into the code. We can just do call delete old. Delete old. And I think that's just going to, I don't know if I need brackets there. It's just going to, okay, we'll see what it does. So see there, you ran it. Now what if we go to longer time, 10 seconds? What it's doing there is it's deleting the previous run. So like before I would have changed this. So there was data going down to 10 seconds and you're getting a crap graph. But if you do this, it's sorted. Okay. So that you actually don't have to do the automatic selecting. Okay, where are we off to next? So yeah, so let me just answer these little questions. I think the exercises, what I'm probably going to do for the exercises is they're quite similar, is I'm going to tell you what the answers to these should be. I think that's probably what I'll do. Okay, so let's do these. So let m equal to 2, let lambda be 0.2, let v0 be 10, u is the initial speed, h be 0.05, and run it. Okay, so give an approximate value for this. So all you have to do is just go down to, no, I need to go a bit further there. So I need to go to maybe, let's say 11 seconds. So v of 10 is the velocity at time 10, 3. Well, we can't be too precise anyway, so let's say 3.67, presumably meters per second. Okay. Next one, look, mass equal to 2, lambda equal to 0.7. Initial speed is 0, which is funny. Now, I know actually that the 0 is not really supposed to be there. It's the next question. Now, it says big time, so let's just change this to, say, 2. So it says big time, so we can just put in whatever we want. So let's say 200 seconds. I think we can see what's happening. What's happening to v of t for large times is just equal to 0. And what does that mean? Well, if you've got a damper, the speed, it's going to stop. That's all it's saying. Let's look at the next one. Mass equal to 0.1. Lambda equal to 1.5. v0 equal to 0. Again, that's incorrect. Equals 2. Then let's do h equal to 0.5. And a final time, that's the big T. Let's see what happens. So this is nonsense. Absolute, complete garbage. A damper will not do this. So what do you want to say? The errors are going mad. Okay, so how can you fix the issue? Now, you got to think, like, if you're talking about an actual damper, the mass of the damper, you can't change. That's not the issue. Even though, like, if that m was bigger, you wouldn't get this issue. So, for example, if I go to 5, I get normal behavior. But you can't just change the mass of the damper if the damper is what you're studying. You can't change the strength of the damper. You can't change the initial speed. The things that you control, you can. The final time, you chose that. But I mean, if you want to find out what's going on at bigger times, look, you're getting nonsense. The thing that you can control is the step size. We learn in lectures that the smaller the step size, the more accurate it is. So if I try 0.05 maybe, I'm getting something that is at least reasonable. Okay, so the issue in the previous part can be addressed by picking a smaller step size. This one is the final one where the u equal to 0 I think is actually correct. So m equal to 2, lambda is 0.2, 0, h is 0.01, final time is 5. Explain the behavior. Well, the velocity, if it starts with no velocity, the damper, nothing happens. Like the force in a damper comes from velocity. And if there's no velocity, there's no force. If there's no force, there's no acceleration. If there's no acceleration, there's no change of velocity. It stays the same. Okay. So I think that's probably all I'm going to do at this stage.